This last style of KSP problem is called the common ion problem, and it deals with the fact that if you have a solution and you're trying to add something that has the same ion in it, it's going to make it less soluble. So I have the example here, sodium chloride dissolving into sodium and chloride ions, and then silver chloride dissolving into silver and chloride ions. Now, since they both have the chlorine ion present, those are common to both of them. So that is the common ion. By trying to dissolve a silver chloride solution in a sodium chloride solution, we're going to actually be able to only dissolve a little bit of the silver chloride, much less than you normally would, because this extra chlorine is essentially forcing your equilibrium away and sending it to the solid side, based on Le Chatelier's principle. Alright, so just like in any other example, we have a sample problem which says find the solubility of copper iodide if it is copper 1 iodide if it's dissolved in a 0.01 molar solution of NaI. So in starting this problem, we're going to start with our dissolution equation for both of these substances. Now the NaI, we know, since this is a group 1 metal, group 1 metals are always soluble, we're going to do a single-headed arrow for that one. And for the other one, we're going to use a double-headed arrow because copper 1 iodide is, it's not completely soluble. Cu plus and I minus. And you'll notice that they have an ion in common. They both have the I minus. So I'm going to write my KSP expression for the copper iodide. So KSP is equal to the concentration of Cu times the concentration of I minus. Now I've looked up the KSP for this, and the value is 1.8 times 10 to the negative 14. Alright, so we know that when there's an ion in common, it's going to decrease the solubility of the copper iodide because this common ion is going to force the equilibrium away. And so it's going to favor the solid. And so we're going to keep that in mind when we go about solving this problem. So the next step is to let X equal the amount of the uncommon ion that will dissolve. So we're going to say that the copper ion here is our uncommon ion, so the amount that can dissolve is X. Okay, so I'm going to plug into my KSP expression. The amount of copper that will dissolve is X. Now, the amount of iodine that will dissolve is also X, but we also have 0.01 molar of the NaI solution, which gives us 0.01 molar of the I minus. So that's going to go into our KXP expression as well. And we're going to set that equal to 1.8 times 10 to the negative 14, which is our KSP value. Now, to make the math easier, we can say something about this bracket here. Okay, we know that X has to be really small when compared with 0.01. Okay, we can say that X is much less than 0.01 molarity. Therefore, since we're adding these, X plus 0.01 is going to just equal 0.01. That's like saying if you had $1 million and you added 25 cents, it's not really going to change the magnitude of your wealth. Okay, so we're going to simplify this expression, so it's just going to be that KSP is equal to X times 0.01, and that's equal to our KSP. Now you don't have to do this, but if you leave the term in there, then you have to solve for x squared. It becomes a little more difficult. It's very manageable, but for ease we can simplify it. And you'll notice that even if you leave it in there, the value you get will still be the same, because this assumption still holds true. Okay, so now all I'm going to do is I'm going to solve this. I know that I can divide both sides by 0.01, and that's going to give me my value for x. So x, which is the solubility of the copper iodide, is equal to 1.8 times 10 to the negative 12. And if you want to go back and check the assumption we made, you could take this value and plug it in right here. And since x is really small, we can say that that assumption was correct. Okay, so x is the amount that will dissolve, and our solubility is 1.8 times 10 to the negative 12 molarity. And if it asks for it in grams per liter, we could change that to grams per liter. And I've just seen a typo. This should be solve for the solubility.